Hello, and so today we'll be talking about how to calculate derivatives in Wolfram language. And how I have divided my session today is I'll talk about the definition of derivative first, then we look at a couple of functions available in Wolfram language, and then how you can visualize these derivatives, find the slope of the algebraic function, and then develop an interactive example to show and calculate the tangent line to the specific function. And in the end, I will also talk about the product rule and the quotient rule, because I've seen many people just confuses it. And so I wanted to make it clear by giving some examples today. So let's start and look at what derivatives are. So basically, derivative is a function related to f of x that will tell you the instantaneous rate of change of f of x, or basically the slope of a tangent line to that function at any point along the curve. There are several different notations you will find across in the textbooks as well, the way you can visualize, you can define the differential equations. And derivatives are very useful in many quantitative subjects like physics and economics. Like, the acceleration is also the derivative of velocity. So how in Wolfram system work is exactly the same as in standard mathematics. So in Wolfram language, we have a function called function d, which allows you to differentiate with respect to some variable. So this is how you're gonna represent the function d. Then there will be square brackets. Then there will be a function f or expression or your trigonometric value or whatever your expression or function is. And then with reference of you want to take the derivative. So the first argument is the expression or the function, or it can be a list of functions as well, which you need to be differentiated. So here is an example of how you can do that. So you just write the function d, function argument comes in square brackets. 3x square is my expression or function, and I want to take a derivative of it with respect to x. And when I can execute it, I will get the result for that. Similarly, in this case, I have trigonometric values, sine of x minus 2 cos of x, and I want to differentiate it with respect to x. So this is the same way you can enter in Wolfram language. You can also use this character over here, and how you can define this character is if by pressing the escape sign and then you type PD and then escape button again, you will get this. Then you press control and underscore, so it will give you a subscript, which you say, okay, I want to do it with respect to x. And then you give the value of whatever you want to do over here. So for example, I want to do 3x squared. So I'll give this that I want to take the derivative of this function. And this is the same result as over here. So you can use this notation also in Wolfram language. So here I can take the derivative of more than one function or expression at a time as well. So we have the same function called d, square brackets for the function argument. Now I have the curly braces, and here I will give it the list of the functions I want to do. Maybe I want to ax squared plus bx plus c is my first one, and the second one may be ax raised to power n plus maybe x raised to power n minus 1 maybe. And then I say, okay, I want to do it with respect to x. And I can solve this and I can get the value for that. So I can also do it in the form of multiple expressions or functions together as well. Similarly, when you have to take higher order derivatives like second order derivative or third order derivative or till the nth order derivatives, you can use another function called d, and then you can just let Wolfram know to till which n you want to take the derivative. So maybe I want to take the second derivative of a function, and I say, okay, my function is cos of x, and I want to do the with respect to x, but I want to take the second derivative. And it goes over here. If I just change it from 2 to n, it will give me the nth order derivative for this specific trigonometric value. Similarly, I can use to find the derivative with respect to more than one variable. For example, I have this function sine xy divided by x square plus y square, and I want to find the derivative with respect to both x and y. I can pass this into the function d, and I can get the result. It's always a good practice to use simplify on this, so that if there is any simplification possible, Wolfram Language will do that too for you. Similarly, we have another way we can define derivatives in Wolfram Language is by using function prime, like f prime, which also represent the derivative of a function of one argument. But in this case, we first need to define the function. So I'm defining a function over here, which is, this is my function x squared over x plus x, and I'll just then say, okay, give me the f prime x, or the first derivative of this function, and it will give me the value over here. As I mentioned earlier, maybe a good practice to do simplify over here. Similarly, if I want to do more higher order derivatives of that, I can do f second prime, take it further, third, f3, want to take the fourth, f4. Always a good practice to in Wolfram Language to use simplify. But in this way you can do it. But might be if you have to take the 10th derivative or a 15th derivative, it might be easy to just use the d function and tell this is my function, this is my with respect to x, and just tell to which level. So if you want to take the derivative of this till 6, you can just mention over here, rather than having so many primes mentioning over there. This is, I find it more comfortable by doing like that. So how you visualize the derivatives is you just directly pass them to the plot function. So this is my function, g of x, and I'm just passing it to this plot function. And I say, okay, give me the g of x, like my function, and the first derivative of this function. And I always like to have this plot legends as expressions, so I can tell them apart. And I also like to add a tooltip, so that when I hover upon these graphs, it will exactly tell me what is which function is this. So you can just directly pass the derivatives and it's the main function into plot function. Now let's see how you will find the slope of an algebraic function. So for example, I have this algebraic function 9x cubed minus 5 of x plus under root of x, and I save it as a AF for algebraic function. So I can just directly give me the first derivative of this, and it will give me the first derivative value for here. And I want to say, okay, I want this at the value of when x is 1. So I can use the replace all command and get the first value, or I can also directly enter. Instead of x, I can just enter the value 1 over here, and I can get the function value from here also as well. And now I can have the plot of the function along with its tangent line. So again, using the plot function, this is my function a of x, and then I'm writing the line of equation over here. So this is the equation for the line, for the tangent line, and I say, okay, give me the range from 0 to 4, and I can see a plot where I have my function across with the tangent line, and I can see that it is just touching the my function at x is equal to 1, which is where I just started over here. Here, similarly, we can define an interactive example for that. So maybe I have this function over here, and this is the equation of the line. And then I can use a manipulate function where I'll call this function and the tangent line, give it a plot range. This graphics is only for this vertex colors, for it to be orange so that it can tell it apart. So it's A is my variable which will be changing the line value, like where the x is. This will be changing from -3 to 3, and I can have them manipulate for this, where I can change the value of x and see how the tangent looks at that specific value of x. So this basically a is my value of x. So I can even give it any specific value. Show me when x is equal to 1, or what happens when x is equal to 2. So I can have a interactive example created. I can take it into the class and I can discuss it with my students why they may see such changes over here. Now, a couple of things where many people do a lot of mistake is the product rule and the quotient rule. So that's why I specifically wanted to touch it a little bit. So do remember that whenever you are taking a product rule, it is not is equal to f of derivative of x of g of x. It's f of x g prime x plus g of x f prime x. So normally people do mistake. They just define the functions like f of x and g of x, and they say, okay, the product will be like, just take the derivative of this and take a product of this, which should be under root x. But remember that this is not how the products of derivatives work. So this is the right definition. I can make the definition over here. Or what I can do, I can take a product. Like I can specifically say this is a product of these two functions. And then when I take a derivative or a product prime of this will give me this similar value as that. And here you can also see that in the plot value over here, where I have the first derivative of x, first derivative of g, as well as the product of both. So this is a very common mistake people do. So that's why I wanted to touch. Similarly, same in quotient. So the quotient rule is not like g prime divided by f prime is divided by g prime. It is gf dash x minus f of x g prime x divided by gx square. So you can do to take a quotient of, like similarly defined in Wolfram language, and when you take a prime, it is similar to as writing the full form and solving it. So do remember these two things because many people take a mistake of that. Let me know if you want to know more about differential finding those. The next topic I'll be touching is doing differential equations and how you can use different type of partial and ODEs in Wolfram language. Thank you. Bye-bye.